Hey, good afternoon, everyone. Welcome to this week 8. Week 8, we'll be looking at the hypothesis testing. Okay, please first look at this slide. We'll do a review. Week 8.1 slide hypothesis testing, null hypothesis H0 and alternative hypothesis H1. Okay, we'll look at this Boston Marathon. Okay, so it says the average finishing time in a few years ago, 2017, was 3.97. Okay, so this is what is known. Okay, we also collected the recent data. What the recent data shows is this is a runner 100 2019, right? So you open it, you saw one of the column called hour. Okay, so this is a 2019, so 2 years later. So the average hour has shown as 3.6 hours. Okay, 3.6 hours. So this is 2019. So in 2017, it's a 3.97. So we think maybe it is a reduced, so everyone runs faster. So we want to prove whether this is true or not true. Okay. So here is null hypothesis generally means status quo. There's nothing changed. That means in 2019, the average hour for the marathon athlete to complete is still maintained as 3.97. So this is H0. And H1 alternative hypothesis will be something of our interest in general. So it may be reduced to 3.6. Okay. So H0 will be the true average hour, or the true mean is 3.97 for 2019. Okay, there's no change from 2017 to 2019. So this is H0. So H1 alternate hypothesis can be either higher or not equal to 3.97. So yeah, so at the meantime, okay. Okay, so here is average finishing has not changed, which is now hypothesis. Alternate hypothesis changed since 2019. In 2019, we have observed the average is 3.6 hours now. Okay, so the true mean is not equal to 3.97, which is an alternate hypothesis. Okay, yeah, so we are going to collect samples. So one of the samples that we see earlier is the sample of 100 athletes in 2019, right? So we want to find using this sample whether we have sufficient evidence to reject the null hypothesis. That means the true mean is not equal to, or we do not have sufficient evidence to reject it. Okay, okay, so that's hypothesis testing. Okay, so or whether to reject or non-reject, we need to look at the sampling distribution of the mean. Okay, right. So based on the CLT, we know that the sampling distribution of the mean will be normally distributed if the sample size is greater than 30. Okay, so here what you are seeing here, my first question is what you are seeing this curve here. What is this distribution? Yeah, this distribution should be the sampling distribution of the mean. Sampling distribution of the mean. Again, this is the data that we obtained. So this is the entire sample of 100 athletes. Okay, so for the 100 athlete, how many mean values do we have? We will only have one mean. The one mean value is 3.6. Okay, 3.6, only one mean. So 3.6 will be somewhere here. So there's only one. But this curve is a imagined sampling distribution. So if we repeat sampling of these 100 athletes again, we'll see sometimes the first one will be 3.6, then the second sample will give us a sample mean of maybe 4.0 or 3.9. So it will in the end it will form a sampling distribution of the mean. But at the meantime, we have a sample of 100 athletes, but we only have one sample mean. Oh, that's very important. So we only have one sample mean. So if this is a sampling distribution, then I want you to calculate the variance or standard deviation. The standard deviation of the sampling distribution, that's a review, right, is called the standard error. Standard deviation of the sampling distribution is the standard error. How do you calculate the standard deviation? SE or SD of sampling distribution is sigma divided by SQRT n sample size. Okay, right? Sigma is sigma. If we know the population, standard deviation. If no, we don't have, then we have the standard deviation of sample to estimate the sigma. Okay, so at the meantime, you know, from this slide, it shows there's a mean of 15 runners, then your n will be 50. Okay, and will be 50. Then the sigma, if it's known to you, then that's good. If it's not known to you, we can estimate from the sample. So in this sample, in fact, we have 100 athlete, 100 athlete, count 100, then average is 3.6. Okay, so if you are using the sample, then we have 100. Okay, in the Excel CSV. Okay, so this is one. Then yeah, we want to reject if the X50 or X100 differs slightly from 3.97. So at the meantime, what we have is 3.6. 3.6 is somewhere here. Okay, then we need to construct a confidence interval around these H0 3.97 with 95% confidence if the sample mean of these 100 athletes or 50 runners fell into the confidence interval, then we don't have sufficient evidence. If they are outside of this confidence interval, which is in the rejection zone, then we can say that we have sufficient evidence to reject. So this is the main idea around it. So, and allow some buffer. The buffer is the confidence interval, and the confidence interval is defined by the confidence level that you want to achieve, whether 95, 99, or 90, right? Okay, then. So this is the first 8.1. Then we'll move on to 8.2. 8.2 is again this marathon. Null hypothesis, the true mean is believed to be 3.97 hour in 2017, and it doesn't change from 2017. So now we move on to here. So rejection zone. Okay, what is the rejection zone? So now assume H0 is true. You have 100 athletes. All right. So from the Excel, we have this 100. And sigma is known to these. So this is what I calculated and provide to you for this example. What it is, sigma square is the population variance. So population variance is this value, HR square, R square. Okay, now, then what it is? What it is showing to you? X n bar n equal to 100. X 100 bar follows a normal distribution with mean value of 3.97, and this is the variance. What is this variance? This is the variance for the population or sample or sampling distribution. This is the variance for the sampling distribution, okay, because it is a variance of population divided by n. Okay, so it is this variance of the population divided by sample size 100, so get 0.043 there around this now. So okay, so based on that, we're constructing a confidence interval. Okay, so we'll find that for a 95% confidence interval, you will find the critical value of 3.84 and 4.10 hours around there. So that's the one within this range is the confidence interval of 95% confidence. And in the RR, which is a rejection region, then left side is 2.5%, right side is 2.5%. Okay, and 3.97 plus minus 0.13. What is 0.13? 0.13 is the margin of error, ME. Okay, so mean plus minus margin of error is your confidence interval, and margin of error is the critical value, CV, times your standard error. The standard error is the standard deviation of the sampling distribution. And the standard deviation of the sampling distribution or standard error is square root of this variance of sampling distribution. Okay. Very good. So we move on next. So type 1 error. So we are now talking about type 1 error. Type 1 error is there's a chance the sample mean will fall into the rejection region while the H0 is true. H0 means in 2019, the average running hour is 3.97. So this is our hypothesis. Okay, if in 2019 it indeed is true, you will observe a gray curve. So this gray curve is a sampling distribution of the mean. Okay, with the hypothesis of true mean average hours in 2019 is 3.97. So it will be centered here, and there's two sides. Okay, then the gray curve is the sampling distribution, and this is a formula there. Okay, then okay, that's what. So now I want to calculate what is the probability of type 1 errors. That means in this gray curve, when you collect samples of 100 runners again and again, sometimes the average hour will be here, 2.97. Sometimes 4.0, sometimes 4.01. It can be anywhere around this x-axis. So there occasionally it will be going to more than 4.1. Sometimes even the true average hour is still 3.97. Due to some randomness when you are collecting the sample, it's still possible that some average hour can go to this position, this point and this point. Okay, so between 3.84 and 4.1 is the 95% area, and the curve on the two sides is 2.5. So when they land into this rejection zone, how much probability that you have? So then move on how to calculate that one. So how to calculate is based on the alpha that you define. Okay, rejection zone is defined based on your alpha. Alpha is a significance level, right? So it's 1 minus your confidence level, and our confidence level is 1 minus the alpha significant level. So 0.05, this is actually what you define in the very beginning, okay? So once you define 0.05, this will actually be your type 1 error. Okay, so I want to achieve a confidence of 95%, then you will calculate that the confidence interval will be 3.84 to 4.1. Okay, how do you calculate this one? You use this formula. So we do a quick calculation. Where is my R? Let me try to find my R. Okay, R is here. Let me do this. We have this sampling distribution, right? So we want to calculate the confidence interval, okay? So confidence interval is confidence interval is first you calculate margin of error, right? Margin of error is your critical value times standard error. Okay, so we need these ingredients. Critical value at alpha equal to 0.05. Okay, critical value alpha equal to 0.5, then confidence level will be 0.95. Okay, now so you find the critical value is Q norm. Also, Q norm P probability is want to find the critical value, right? So critical value is 0.975. Okay, because there's 2.5 area here. So basically, we want to find this one. Then the area to the left of this red cutoff line will be 2.5 plus 95 in the middle, so 0.975. Then we use Z distribution. We just use Z distribution. Okay, so we do a more orthodox way. So this is your Z score. So this is a critical score, 0.96 or 1.96. Okay, so we have CV, then the SE. What is the SE? SE is the standard deviation of the sampling distribution, and it's a square root of variance, SQRT of your variance. So your variance is here. This is your variance. This is your variance. Okay, this is your variance. So your SE is this value. Okay. Yeah, right. So your margin of error is this one times SE. So ME, let's display ME. ME is 0.13, basically 0.13, right? So this is what we see here. Earlier 0.13 plus minus 0.13. Okay, here. It is as 3.97 plus minus 0.13. So basically, I'm actually recalculating this confidence level first. Okay, I recalculate the confidence level. So now you use X bar 3.97 plus your ME is the upper bound, minus ME is the lower bound. So you have 3.84 to 4.1. So this is your CI upper limit. Then this is your CI confidence interval lower limit at 95% confidence. Okay. So this is your confidence range. So outside of this confidence interval, is your rejection zone. Okay, rejection zone. And two sides, each tail is 2.5%. Okay. So now we have understand this. Then we look at samples. Okay. If the sample mean falls within this confidence interval, it is not in the rejection zone, then we do not have sufficient evidence to reject the null hypothesis. If the sample mean actually inside this rejection zone, then we have evidence to reject it. So look at that. The sample mean calculated based on this 100 runner is now 3.6. Okay, 3.6, it will be here. It will be lower than 3.84. It is in the left side of the rejection zone. And we have sufficient evidence to reject the null hypothesis. Okay, so this is about the null hypothesis here. So 3.9, 3.6 will be here. So that means we have evidence based on the sample and the sample mean 3.6 to show that the 2019 runners average hour to complete the marathon is not equal to the 2017's average 3.97 hours. Okay, so whether it's lower or higher, then we'll look at it later. So at the meantime, it means equal or not equal. Two-sided test. Then next, we'll move on here. Let's say we increase the rejection zone. So if we increase the rejection zone, that means alpha is bigger. And you maintain a lower confidence. Also, your alpha is bigger, you are more likely to make mistakes. So it's easier for a sample mean of 100 runner to fail into a rejection region. It's more likely. So the area will be larger. So this is what is saying that. Okay, so move on. Hope you are okay at the moment. So this is called type 1 error, false positive. So then we move on to type 2 error. Type 2 error is when H0 is actually false. There's still a chance that sample mean will not appear in rejection zone. Then we fail to reject H0 while it is false. Again, we don't know whether the error has happened or not because we do not know the true mean, where the true mean. Or we have a sample of 100 runners in 2019, but we don't have all of them. Okay, that's why the true average running hour for all the runners in 2019, we do not know. Okay, and that error is called type 2 error. So what is the probability of type 2 error happens if the true mean is actually 4.0? Okay, so this is what we need to learn here. So the gray one is the H0. Okay, so H0. If H0 is true, then you have this gray curve. So it is 3.97. and we have find the rejection zone. So now what we are saying is, what if the actual true mean is 4.0? 4.0 is here. 4.0 here, the blue cutoff line. That means in 2019, we assume if the population mean is 4 hours, population mean is 4 hours, then if that is the real case, you will observe the sample means to follow the purple curve. So the purple curve basically is the gray curve you shifted to be the mean at 4.0. So they have the same variance because we have the same sample, same population. So the variance, the standard deviation, the standard error should all be the same. So basically this blue curve is just a shifted gray curve, okay? So if this is the case, we're here, then you are going to observe the sample mean to appear either here, more likely to appear in the center and less likely to appear on two sides. So now take note of it. If you get a 100 runners, average hour, say to be 5 hours, just say 5 hours, 5 hours, and the true mean is 4 hours. So the 5 hours will be here. It will be in the rejection zone of the hypothesis 0, mu equal to 3.97. So it's 5. So it got rejected. That means the sample data tell us the average hour in 2019 is not equal to 3.97. That's okay. That's cool, right? We didn't make mistake because they are predicted or tested as not equal to 3.97. It's in the rejection zone, okay? If due to some reasons, you have a sample mean calculated at 3.6, let's say 3.6 here, when the true mean is 4.0, it's still possible because it's a bit extreme, but it's still possible. Then it goes to the left side of this rejection zone, and you still reject it. And the nine hypothesis mu not equal to 3.97 will be rejected. That means the true mean of 2019 is different from 3.97, which is right? Because the true mean is 4.0, it is actually different from 3.97. So as long as your sample average still stay in the rejection zone, you are still fine. Your test didn't, your test result is reflecting the truth. It only have some problem that if your sample mean is landing in between 3.84 and 4.1, which is outside of your confidence, outside of your rejection region and inside your confidence interval for your H0. What if it lands here? If it lands here, then according to the hypothesis 0, we do not have sufficient evidence to reject the null hypothesis. Then we accept the alternate hypothesis. Alternate hypothesis is, we do not have, we do not have the sufficient evidence to reject the null hypothesis. Then somehow, loosely speaking, we say, hey, it's highly likely the average running hour in 2019 is same as 3.97. So this is our conclusion, right? Then this conclusion is wrong. It is against the reality because the reality is the true mean is 4.0. It is different. So the real reality is they should be different. But the test, after testing, since this sample mean is not in rejection zone, then we make a mistake. And this is a mistake called type 2 error, type 2 error. So where can we find them? How can we calculate these type 2 error? How do we quantify it? So the type 2 error is in the area here. It is under the purple curve. It's under this purple curve in between these two red cutoff line. Okay, it is there. So the area here, So we need to calculate the area showing here. Then that is it. Type 2 error. Okay, so now let's look at how do we calculate it. So we know this blue curve, this purple curve follows a normal distribution. Purple curve is centered at 4 point. Sorry, centered at 4. Yeah, mean value equal to 4. And your standard deviation or standard error of is 0.066. So that's actually what we calculated earlier. We'll get the standard error 0.066. Okay, so it is a square root of 0.0043 5. Okay, so that's it. So basically the area to the left of 4.1 minus the area to the left of 3.84 is the area of this type 2 error. Okay, so take a while to digest it. So first is we need to define an alpha. Alpha determine the confidence interval and the rejection region that we define first. Okay, it can be 5%, 1%, or any arbitrary significant level. Then after that, we'll find the critical value there. Then based on this critical value and the true mean of the actual marathon, which is 4 hours different from the 3.97, then we can calculate the area under the curve here. Okay, so that's your type 2 error. Then my question here, where is your type 1 error? Okay, where is your type 1 error? Your type 1 error is the rejection regions area, okay, of this gray curve. Okay, so the gray curve is your type 1 error. So the rejection region is 2.5 plus 2.5. This is actually what you define here. So with a certain type 1 error, we want to calculate what is a type 2 error. Okay, so now we just need to calculate P norm this one. I'll calculate this one now. Fine. Just show you a demo. So this is a type 2 error. So your SQRT square root SD is 0.066. One moment. Argument X, okay, P norm, not X, P norm, Q equals to 4. Sorry, X, Q equal to 4.1, Q equal to 4.1. Okay, then mean this. Okay. So this is the area 0.935 is the area to the left of 4.1. Okay, then what about 3.84? 3.84. Run it. So the area to the left of 3.84 is a small area. Then you use the first one to minus the second one. Then you got 0.9274. So the area here will be 0.9784. Nine, 9275. 9275. Okay, so that's the area that you can find. Okay, so that's the area that you can find. Okay, now I hope you are better in understanding the type 1 error and type 2 error. Type 1 error is your alpha that you define. Type 2 error that it will change based on your true mean. Okay, in general, in the question, it will tell you what can be the potential true mean. So then your blue curve will move along this x-axis. Sorry, not blue curve. The purple curve will move. So when your purple curve is moving, your gray curve doesn't move. Your rejection region doesn't move at all, right? So your height H0 3.97, this one will not move. Only your purple curve will actually move along this x-axis depending on what is the actual true mean is. Okay, then let's move on to the next one. So in this scan, rejection zone is in this form. Okay, it's saying that if your rejection zone is increasing, your rejection zone is increasing, so your blue curve stay there. the shape and the standard deviation of the gray curve is stay there. The shape will also not going to change. It won't get fatter or slimmer because your standard error has been defined. So the gray curve will be there. And at the meantime, your alpha is 2.5 that you define that is smaller region on two sides. Let's say you're going to increase from a rejection region from 2.5 to 5%. So 5%, you add them into the 10%. The one in the region in the middle will be less than 90% of under this gray curve. So when this happens, your rejection zone increase. So your alpha increase from 0.05 to 0.1, 10%, right? Then your type 1 error will increase, right? When your type 1 error increase, these two red curve will go into the center, right? The two red curve, a red cutoff line will go to the center. When these two red curve gets nearer, the area under this blue curve, under this purple curve will get smaller. So that area is your type 2 error. So when these two cutoff line goes nearer and the rejection region goes larger, your type 2 error will get smaller. Okay, that's it. So, and vice versa. Okay, so this is the last slide, what it's trying to tell you. Okay, so when rejection region goes larger, your type 1 error goes higher, your type 2 error goes smaller. If your rejection region from large to small, then your type 1 error alpha gets smaller. So your type 1 error gets smaller. Then since this region confidence interval gets larger, then the area that you can cover the purple curve gets larger. So your type 2 error goes higher. Okay, so these are the few key things that you need to be aware. Okay, so it's a bit it will take some time for you to digest. Okay, so now next let's move on to these tutorial questions. Okay, tutorial question of week 8. Specify the null hypothesis and alternative hypothesis. A study tries blah, blah, blah. So this is one. So I have some reference solutions here. The reference solution is in the form of R code of week 8 R tutorial solution. So it will be released to you when you have access, you can read it. So I just copy everything from here. I copy everything. I copy into a Word document for easier reading for you. Okay, so let's look at that. Our implementation. The question 1, it says, okay, a study tries to show the average back to school spending will be different from 600 per family this year. So a study, blah, blah, blah. So the solution is the null hypothesis, the average spending is $600. And the alternate hypothesis is not $600 per family this year. So straightforward. Okay, then second study shows that students exercising at least 5 hours per week achieve a higher average GPA than those who do not. Okay, so we say the mu1 is the average GPA of those students who exercise greater than 4 hours per week, and mu2 at those ones who don't. Okay, so that null hypothesis is mu1 less or equal to mu2. Yeah, shows that at least achieve a higher average. So there's key thing is achieve a higher. So achieve a higher is something that we want to prove and we'll be interested. So if something is interested to us, we generally put it into alternative hypothesis. That's why you are seeing that alternative hypothesis is mu1 greater than mu2. Then the null hypothesis will be the opposite. Okay, so mu1 less or equal to mu2. Then we'll look at sample, collect sample to see, do we have sufficient evidence to reject the null hypothesis? If we have evidence to reject it, then we will accept that alternative hypothesis, and then the alternate hypothesis has been proved, and this is of our interest. Okay, so next is study tries to show the difference existing average hours among a few schools. So your null hypothesis is all the 3 schools are equal. Okay, average of sleeping per night is equal. So if any of the pair is not equal, then that's your alternate hypothesis. Okay. So question 2. Question 2, describe the type 1 error, false positive, and the type 2 error in the following problems. What might be the cost associated with these? So we look at them one by one. So for question like this, false positive, false negative, it's very important. First, you need to define what is the positive or negative here. Okay, that's by definition. We define generally by common sense and by the phenomena that we are interested in. So let's look at the first one. Type 1 error is false positive. The actual or the truth is negative. Then type 2 is false negative. The actual truth is positive. So it's by definition. So in general, we need to first define the positive and negative to a particular concept or the context in the scenario we're analyzing. In general, the rarer event of our interest, or that's the event that we want to study is we generally define positive. So let's look at the first thing. First one is medical test to detect cancer. So for a patient, we really are more interested in knowing that this person is actually having a cancer so that we can treat it. If that person has no cancer, we don't need to worry too much, right? So we really worry and care about whether the patient has cancer. So we are doing a test and we define having a cancer as a positive. So the test and diagnosis showing or telling us it is a cancer, then we define it as a positive event, okay? But whether this patient is really having cancer cells in that patient's body, that's called ground truth. We don't know at the moment. We only do a test. Let's do a blood test. So it's indirect examination, indirect classification. So that's how we can define what positive or negative. So the negative is the test. The blood test tells us the indicators indicate no cancer or low likelihood of cancer. Okay, indicate that the patient is healthy. But whether the patient really have cancer or not, we do not know. Okay, so type 1 error is a patient is tested or diagnosed with cancer after blood test, but actually the patient is healthy. There's completely no cancer cell in the body of this patient. Okay, so the ground truth is the patient has no cancer cell, but the test was wrong. The test indicated it has cancer, that the patient has cancer. And this is called a type 1 error, okay? False positive. Why it is positive? Because a test shows positive. And it is wrong, so that's false positive, okay? So the cost associated with unnecessary medical treatment, they go through the chemos and do a lot of tests, right? Then in the end, the patient spend a lot of money and suffer a little bit, but in fact, it's a useless treatment. Okay, type 2 error, okay? So the patient, in fact, has cancer. In fact, has cancer. Then the blood test shows no cancer indicators. Okay, again, this is a mistake. This is called false negative. So the test is tested as negative. Doesn't have cancer, means healthy, that means negative. But again, this is wrong. That's why it's called false negative, or it's called missed cases. The patient has cancer cell in his body, her body, but the blood test shows no indicator. So this is called type 2 error. Then what is the cause? The harmful side effect and emotional distress and delayed treatment and so on. So loss of lives. Okay, we're fine with the first one. Okay, then second one, criminal trial where a defendant is accused of murder. Accused of murder. Okay, here. So the positive is the trial decision from the jury. The person is guilty. The person is guilty. Then the negative is the trial decision is no, not guilty. Not in this, not guilty. Not guilty person. Okay, not guilty person. So the type 1 error is the person in fact is innocent, didn't do anything wrong. That's the ground truth. But the jury and the court find based on evidence, so evidence may be wrong, find the person is guilty. So this is called convict an innocent person. So that's a false positive here, okay? So again, you define the positive. You can swap the positive and negative. Then your type 1 error and type 2 error will swap as well, okay? So the type 2 error in this scenario that it's a guilty person, okay, and a acquitted, because we do not have sufficient evidence to prosecute this person. Do not have sufficient evidence to prove that that is guilty person. So that's a type 2 error, so missed cases. Then what are the associated costs associated? So again, third one, quality control chips for a chip in a phone manufacturing plant. So the chip may have some defect, okay? So the defect is through test, okay? Some X-ray test or whatever test on the during the QC quality check. So if the test statistic shows, okay, you are pretty low on this measurement, then we classify this chip as a defective or bad chip. Then the negative is, we accept it is good chip. It passed the test, basically. Then type 1 error is, you have a good chip. Actually, it's usable because you can use this chip, but some indirect tests that showed wrong. This chip is defective. So this is a good chip wrongly classified as defective. So this is your type 1 error. Then the type 2 error is, in fact, it is a bad chip. You get this chip, you plug into your motherboard on the CPU or the phone inside, it doesn't work. So it is a bad one. But the test has passed. It said, it passed this production line. So this is a bad chip wrongly classified as an acceptable one. So this is a type 2 error, okay, in this scenario. Then we move on to this question 3, okay? Question 3. Consider the test of H0 mu equal to 100. H1 is mu does not equal to 100. So this is a quantitative one. So we'll look at that. So the rejection region that we have defined is 90, 100. Okay, 90 and 110. So that's a rejection region on two sides. Suppose the population follows a normal distribution. Again, it tells you the population follows a normal distribution. Then what can you do? You can use Z distribution. You can use Z distribution. And your sample size is this. This is your sample. Okay, how many samples do you have? 1, 2, 3. Well, quite a lot. Quite a lot. Then the first question is, should we reject H0? Okay. Should we reject H0? Should do this. So we find one of these. Let's create one of these. So here is, now you assume 100. Here is 110, right? And here is how much? 90. Okay, so rejection zone, you have rejection zone, and it's not necessary to be 2.5 at the moment, right? So it's not necessary to be 2.5. You don't have these, you don't have these. Okay, so then mu is to say 100. 100. Okay, so the true mean at the meantime. Okay, true mean is say 100. So the true mean is 100. Okay, we'll move it here. True mean is 100. Okay, so your rejection zone, let me see. In fact, your rejection zone, it doesn't define anything. We just say AR equal to this one. We don't know. For this question, actually, we are not touching this quantifying the rejection zone. Oh, we just know 2 point. Alpha, you can define somewhere. We'll look at that one. Basically, you have alpha there. Okay, right. This, so I pass this one here. Yeah, okay. So this is the background. So let's look at question 3. If the sample is this one, then we run it. Then your sample mean is 107.8. Okay, so let's have a look at the length of these. So how many elements do we have? Length. 30. Okay, that's good. Sample size is large, so we use DC distribution. Okay. So now you have a some test statistic calculate here, right? So it is 108. How about 108? Here. 108, yeah, 107.8. So it is within this confidence interval. It is outside of this rejection zone, right? It's outside of this rejection zone. So we do not reject. Now we fail to reject. Okay. So conclusion, since the sample mean is this, then it's not in the rejection zone, then we do not reject. Now hypothesis 0. Okay, so it's straightforward. So this is question 1. Then we'll look at next question. Okay, we'll look at next question. Next is suppose now X is this. Now X is this. X is a population, distribution. Set the seed value to this, draw 1000 sample means, then to calculate sample mean, create a histogram of the sample mean, calculate sample mean statistics, number of times that H0 was not rejected based on the above rejection region. Okay. Okay, now let's look at this theory first. Okay, now we are saying that we have a population. We have a population which in fact the mean is here. Your true mean is now 95. Okay, now true mean is 95. It's no longer here. It's no longer here. The true mean is 95. Your null hypothesis is still your mu equal to 100. It is here. It is here, right? So now, but your true mean now is 95. 95, the purple one, not the purple one. So before we move on to all these, let's do these set seed. So let's have a look at the population mean. So we need to get n equal to 30. So okay, let's first have a look at the population mean. So I do a random sampling, then mean equal to this, then deviation equal to 15. So this is the population. So we do a population, but there's a lot of random numbers, right? So we do a histogram. Histogram of these random numbers, so many random numbers. So we are seeing, so this is a population distribution. So the center at 95. Okay, so basically this is the purple one. It's a purple one. Then we are going to draw samples from this population. Okay, so another way to look at this is instead of using this, we use a denom x equals to a wide range minus 1000 to 1000. Then mean. Give you a better view. Okay, and see what it says. Okay, standard deviation, unexpected, sorry, too many. Okay, so there are a lot of numbers. I think the number is a bit too much. There'll be about 20 to 160. 20 to 160. SCP from equal to 20 to 160 by 0.1. It is SCP function. SCP. And what is that? By equal. Could not find function. Yeah. Separate or REP. SAP. Replicate. Replicate. It is this one. Okay, let me do this. I want to do it. Yeah, sometimes I forget. Then ask AI. Okay, let's quickly ask AI. Do so. SEQ, yeah, not the SCP, sequential SEQ. SEQ. Okay, good. So now we have this one, then I want to plot it. Here, OT. This is X equal to this, then Y equals to this. Then I have a bracket. Okay. So basically, this is a density function of your population. Okay, so I just show you a different OER. This is a density function. Your center as the 95. Okay, so now we are going to draw samples from it. It says we're going to draw 1,000 random samples and the sample size equal to 30. Calculate the sample mean. Okay, so the code I don't explain, so you will need to look at that. Is I create a sample mean, then I loop 1,000 times. Then the sample mean will be stored as mean value and R norm get 30, sample size 30 from this population distribution. So each time I get 30, mean for 95, standard deviation 15. Then I calculate the mean value after that, I store into the first sample mean, and I repeat this 1,000 times. Okay, so set C this, repeat 1,000 times. Then after that, you're going to see so many sample means, right? So many sample means. You are seeing the sample mean here is number 1 to 1,000. So there's 1,000 numbers. Each of them is a mean value. So the histogram of the sample mean is the sampling distribution of the mean. So whatever you're seeing here is the sampling distribution of the mean. Okay, so what do you see here is the sampling distribution of the mean, right? Then the standard error, just empirical standard error is the standard deviation of the sampling distribution of the mean. So this is by simulation. Okay, so what is your SE? SE is 2.84, around 2.84. Okay, so the standard error is the standard deviation of the sampling distribution, and the sampling distribution's standard error, the standard error should be equals to your population sigma, your population standard deviation sigma divided by SQRT sample size 30. So you just verified your sigma here is 15. So we just use 15 divided by square root of 30. We should get a similar value to the standard error that we are obtaining through the simulation. So 2.7 is the theoretical standard error. And through our simulation by drawing 1,000 calculating 1,000 sample means, we find these charts standard error, a standard deviation of the sampling distribution is around 2.73, is 2.8. So again, this is the review. So earlier you are seeing this is your population distribution. Mean 95, standard deviation of this population distribution, sigma is 15. It's 15 we define here, it's 15. Then now the sampling distribution, the standard error will be 15 divided by the square root of sample size. And we verify it is correct. Okay, so now we have this histogram showing you sampling distribution. Then we want to find out, okay, what is our region here? We're talking about these 90 to 110. 90 to 110, right? 90 to 110. 90 to 110. How many are outside of them? Based on the sampling, 90 and 110. 90 and 110. How many are within them? Okay, how many are within them? So we want to find out how many are within it. So we do this. This is lesser than, oh, sorry. This question is asking about calculate histogram. Not rejected based on, not rejected. Okay, not rejected is Okay, not rejected is in between 90 and 110, right? So in between 90 and 110. So what we will do is we find in between, lesser than these, lesser than 110. Yes, all of them are lesser than 110. How many are lesser than, say, 90? 30 are lesser than 90. So we use this one minus this one, you will get 970. So there will be 970 in between 90 and 110. So the ones in the purple curves area in between these two cutoff red lines will be 970 sample means here. Then here in the left tail, there will be 30. In the right tail is 0. Okay, it happened to be these. Okay, based on this set seed. Okay, you can also calculate using the next formula. It will also give you 970. Then you divide by 1000. So your total will be 97%. Oh, so this is a question 3.2. It says calculate the summary and the percentage of times that H0 was not rejected. The H0 was not rejected when your sample mean is in between these two cutoff lines, not rejected, right? So we have 1,000 sample means. We find out how many sample means are within this region and how many are in a rejection region, right? So retain those ones within this 90 to 110 range divided by 1,000 is the 97%, okay? This is 97%, okay. Okay, when you do a summary, you see the maximum is 104.37. 104.37 is lesser than 110. Maximum is here, lesser than 110. So that means there's no data points, no sample mean larger than 110. Okay, it happens to be like that. Okay, so this is the 3.2. 3.3. Suppose, again, 3.2, the area here is your type 2 error. Okay, the type 2 error. When your true mean is actually different from your H0. When it's actually different, but you fail to reject 97% of time. You fail to reject because we're calculating the purple area, which is a type 2 error. So 3.2, the percentage is your type 2 error. Type 2 error, when you already know your rejection source, where your rejection source. Okay, now, now 3, suppose X, the population is actually centered at a mean of 100. And we draw the sample means. Okay, so then we do again, we show you this one. Okay, 3. Now we say that succeed, then your now mean value instead of 95 become 100. Okay, so we do this. Succeed and populate. So now this is your 3.3 population distribution. It is centered at 100 with a standard deviation of 15. Okay, and your null hypothesis is your population mean is 100. So this actually this time is showing your population mean. In fact, is 100. In fact, it's 100. Then we collect 1,000 sample means. After we collect these 100,000 sample means, we do a histogram to show you the actual sample mean. So you notice, so this is the population distribution centered at 100. Then this is the sampling distribution of the mean. Okay, sampling distribution of the mean. And the standard error or the standard deviation of sampling distribution of the mean is your population sigma 15 divided by square root of 30. This time we can verify again. You will see it may be still similar, around 2.73, 2.8, 2.7, around that, right? So this is the actual simulated standard error. Okay, now we can calculate the rest of it. We can calculate the rest of it. This time you're asking to calculate, okay, create history. Number of times H0 was rejected. Okay, H0 are rejected. So this time, we actually have true mean here. True mean here. True mean is 100. We look at the gray curve. Gray curve. So we look at this gray curve. Gray curve is a true mean equal to 100. The population true mean is 100, and the gray curve again here. The two curves you are seeing, they are sampling distribution of the mean. They are not population. They are sampling distribution of the mean. So now you have this gray curve. This gray curve. And you know the rejection zone are either lower than 90 or higher than 110, right? So basically, we are going to count how many sample means out of this 1,000 fell into the right rejection zone and the left rejection region. Okay, so this is what we are going to calculate. And you are going to calculate these two parts are your type 1 error. Type 1 error. Where is the type 1 error? Your type 1 error should be shown here. It should be a type 1 error. Let's show here. But the error rate we do not know at the moment. Oh, actually, we do not know. Later can show you. Yeah, we're going to calculate these two. So how many are smaller than 90? We'll calculate how many are smaller than 90? 3. How many are greater than 110? 0. Okay, sum them together. 3 plus 0 is 3. So 3 sample mean here, 3 sample mean, 0 sample mean here out of this 1,000. So your type 1 error is 3 plus 0 divided by 1,000. 3 plus 0 divided by 1,000, it is 0.003 or 3%. 3%. So in fact, here we can reverse calculate this alpha is 0.003. Actually 0.3%. It's a small number. It's a very small number. Okay. 0.003, and your type 2 error is beta B equals to 97. 97. This is what we calculated earlier. Okay, so that's 3.3 and 3.2. 3.3 and 3.2. So 3.2 is your type 2 error, false positive or false negative. This one is your type 1 error, false positive. Your alpha equal to 0.003. Then your beta equal to 0.97. This is what we calculate. We'll calculate. So equals to 970 divided by 1,000. Here is equals to 3 divided by 1,000. Okay, so this is what we have calculated so far. Okay, then the question 4 is asking how the percentage 2 and 3 are related to type 1, type 2 error. So during, we have just explained, right? So 2.2 is your type 2 error. 2.2 is your purple curve. Okay, the purple curve is your true mean equals to, purple curve is your true mean equals to 98. 95. Okay, so when it's 95, it's different from the actual null hypothesis. And we want to calculate the area under the blue curve outside of this rejection region. So that is your type 2 error. Okay. Okay. Now, then your 3.3 is your type 1 error. 3.3 is your type 1 error. when you're calculating type 1 error, you'll find that the true mean is 100. Your null hypothesis is also true mean equal to 100. And what is the number of sample means can potentially fall into the rejection region? If they fell into it, that means, wow, we just observed some very extreme. We're just a bit unlucky. We're just a bit unlucky to make this mistake. That got rejected, but actually the true mean is 100. There are occasionally small chances the sample mean can go to very extreme regions, even when your true mean is 100. But the chance is very small. It is 0.003, 0.3%. Okay, so that's your type 1 error, your alpha. Okay, so now next we are moving on to something more hairy. So if we change the rejection region from 90, 110 to make it, is it larger? Yes, make it larger. 3.5 is make it larger. So we are increasing the rejection region. You increase the rejection region. Yeah, right. So increasing the rejection region. So by theory, we know when you increase the rejection region, your type 1 error will go larger because the rejection region larger is more likely for the sample mean to fall into this rejection region now. So that is the case shown here. So you are changing from the red rejection, orange rejection region to the green one. So rejection region gets larger. Then you should have higher type 1 error and a lower type 2 error. Same here. This is type 1. This is type 1 error. This is type 1 error. So now we are actually working on this. Type 1 error, whether type 1 error and type 2 error will increase or not. Okay, so let's look at type 1 error. Basically, you move these two lines here. You move these two lines here. Right, then the area under this gray curve outside of these two red line gets larger. Gets larger, right? And then the area under this purple curve gets smaller. So type 2 error will get smaller. So that's the visualization. Then we use R to calculate it. Okay, so we move on. Question 4, you are going to read a little bit of here. Yeah, that's question 5. False positive is type 1 error. Type 1 error. So we are again using the C, the blah, 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 calculate, right? Then after that, we calculate, okay, the rejection. Again, we do the sample. We do the sample, then we calculate and prove it, okay? Histogram is this, then it's centered in 100. So we're processing the type 1 error first. So sampling distribution of the mean centered at 100. Okay, now earlier we have calculated if the rejection region is 90, 110, we'll get 0.003 type 1 error. Okay, now let's say I make the rejection zone larger, 92 to 108, larger. So I want to count how many sample mean are now lesser than 92 in the left side of the rejection zone, and how many are in the right tail of the rejection region. Okay, so then we divide by 1000. You are going to see that your type 1 error is now 0.007. So it gets increased from 0.3% to 0.7%. Earlier is two sides is 0.3%. Then now you make the rejection zone larger by moving these two cutoff line to the center. Then the area on the two tail gets larger. And the quantified value is 0.7%. Okay, so now we'll move on to the false negative. False negative is you change the mean value from 100 to 95. 100 to 95, right? So basically this one. 195. Again, you move this one from 100 to 108. Then here is from 90 to 92. So the area under this blue curve within these two red cutoff lines gets smaller, Earlier it was 0.97, very large, 97%. Then it should get smaller. So let's look at that. Again, we draw 1,000 sample means. We plot the sample mean. You are seeing that it's centered in the 95. It's centered in 95. So basically, it's the blue, purple curve here. It's centered at the 95. Centered at 95. Then we calculate. Originally, it is 97%. Then we change this rejection region. Then the area in between gets smaller. So from 97 to 85%. Okay, so that's the one. That's the one. Okay, question 6 is now, the rejection region, instead of getting larger, gets smaller. So basically it's the opposite. Rejection region gets smaller from here. So type 1 is instead of from here, it goes to 88. Instead of 90 here, then 88, then here is 112 is there, so around here. So your type 1 arrow will get smaller. Your type 2 arrow will get larger. So that's quite obvious. Okay, so now let's look at that. Your type 1 arrow earlier is already pretty small, 0.3%. When you make this rejection region smaller, then it will go down even further. And in this example, it's actually got 0 out of these 1,000 sample means. So we have 1,000 sample means. Out of this one, we'll find that there is 0 in this region. So it gets smaller. So this is 100. So then what about the type 2? Type 2 is this. Okay, you make it smaller, from 90 to 88, then from 110 to 120. 112, around 112. So the area under this blue curve gets larger. Gets larger. Earlier it was 97%, right? Earlier it was 97%. It's now centered at 95. Earlier it was 97%. Now it's 88 and 112. You are seeing that it increased further to 99.4%. Okay, that's all for this week's content and tutorial. Another thing is I have also uploaded another reading material, which is you should be able to access from the learning management system. It is an example of false positive and false negative. So to give you a little more examples using the average height of male and female student to help you to understand more about the false positive and false negative, type 1 error and type 2 error. Okay, so you look at that to differentiate what is the false positive, what is the false negative. Okay. And when your rejection region changes, your alpha beta changes, then what is the impact with? Okay. When your cutoff changes here. So basically, this is your rejection zone, the cutoff line. If you move it, then you will trade off between the type 1 error and type 2 error. Okay, so read that one as well. Okay. Thank you very much. That's all. Bye-bye.